Hi, my name is Kevin Tian, and today I'm going to be telling you about our recent work, Omnipredicting Single-Index Models with Multi-Index Models. This is joint work with Lingjia Hu and Chutang Yang. So to give you a roadmap of how this talk is going to go, the first part of the talk will give you an overview of the key definitions used in this paper, as well as our main results. The second part of the talk will talk about our main algorithm, as well as give a sketch of its analysis. And the last part of the talk will overview how we make it sample and runtime efficient. Okay, so to begin, I want to start by recalling the standard setting of loss-based supervised learning. So this is a traditional paradigm in supervised machine learning, and the main characters involved in this definition are a distribution D over a label space, over a feature space X. And today we're going to focus on the case where the feature space is constrained to be the unit sphere, as well as a label space Y taking outcomes in 0 or 1. So this is binary prediction. Furthermore, we are competing with a class script C consisting of comparator predictors that we would like to compete against. In particular, you can think of C as linear functions, for example. And finally, there is a loss function associated with how well we measure our predictions. In particular, this loss function could be squared loss or cross entropy or any number of a variety of other losses. And finally, our goal is to learn a predictor P, which takes in the features and outputs a prediction. And in particular, if our predictor P belongs to this family script C, then we call it a proper predictor, and otherwise it is an improper predictor. And our goal is to compete against the best possible predictor in C, script C, up to an error of possibly epsilon. So the main motivating question in the definition of omniprediction is what happens if we do not know the loss that we would like to measure our predictor against in advance. In particular, this loss could depend on parameters that are unknown at the time of training. Moreover, we might want to measure our predictor using multiple losses, for example, different balances of how much we care about false positives versus false negatives. And from a more philosophical perspective, one might ask the question, what does it mean for a predictor P to measure, y given x? A loss evaluating using a single loss is just one measure of how close we are to the ground truth. But if we audit it with multiple losses, then we somehow capture more generally the ground truth of the expectation of y given x. So this motivates the definition of omniprediction, which is the key definition we're going to study in this paper, where we have a family of loss functions L, a script L, and we want to compete against a optimal predictor from a comparator class against all of these losses simultaneously. So the key additional character in this definition is a loss function family script L, which consists of a number of losses that we want to audit our predictor against. And one interesting facet of this definition is that it also includes a loss-specific post-processing case of L. And in particular, each loss induces its own case of L that we can use to post-process our prediction. This is essentially to handle things such as type mismatches between the comparator class C, which could output any sort of prediction, compared to our predictor P, which is meant to output predictions in 0, 1. One important thing to note is that this loss-specific post-processing does not depend on anything about the distribution and is only inherent to the loss function. So this is a slight technicality that will show up later. And one thing to note is that this definition of an omnipredictor is fundamentally an agnostic learning guarantee. That is, we don't posit that there's anything in this family script C that actually labels the predictions y given x. In particular, this definition makes just as much sense in the agnostic setting as the realizable setting, where we are able to actually label y given x, expectation of y given x using something for the comparator class. So now I want to focus on the specific instantiation of omniprediction that we focus on this paper, which is defined via single-index models. So in picture, this is what a single-index model is, and it posits that the expected label given the features is governed by a composition of a linear function, w dot x, with a one-dimensional monotone function. In particular, this is an example of a semi-parametric model family, where the parametric part comes from the linear predictor w, and here we're going to restrict to linear functions that are bounded in the unit sphere. And the non-parametric portion of the definition comes from the link function sigma. In this talk, we're going to focus on the case where sigma is the family of beta Lipschitz monotone functions from -1, 1 to 0, 1. I want to note that the definition of single-index models posits that sigma is part of the definition. We don't know sigma in advance. In the case where I specify a given value of sigma, this is known as a generalized linear model. And if you haven't internalized this definition, take a look at the picture, which shows that you just line up all of the points in the direction of W, and then you fit them using the monotone function sigma. Okay, so what are the losses and comparators that we use in the omniprediction definition specified to single-index models? Every single monotone link function sigma induces what's known as a matching loss. So in particular, this matching loss is defined as an integral where the link function serves as the antiderivative. One thing to observe is that because the derivative of this is simply given by the link function up to the constant label y, and sigma is monotone, every matching loss is always a convex function. Moreover, you can check using the first order optimality conditions that the optimal prediction t to play in the matching loss is simply sigma inverse applied to the actual expected value of the label. So because of this property of the optimal prediction, every matching loss can be reparameterized using a proper loss function, which takes in values v as prediction space. So namely, v is in the interval 0, 1. And in particular, if y is actually drawn from Bernoulli given with mean v, then the optimal thing to do is just to play the true Bernoulli variable v. Okay, so just to give some examples of this, when sigma is the identity link function, the induced matching loss and proper loss are both simply a rescaling of the squared loss. On the other hand, when the link function is the logit function that rescales the reals into the interval 0, 1 based on how confident you are based via exponentiation, the induced matching loss and proper loss are variants of cross entropy and logistic loss. Okay, so now it's time to define the main question we study in this paper. Our goal is to learn omnipredictors for the family of sims. More precisely, the loss function family we are considering is the family of matching losses for monotone Lipschitz link functions, and the comparator class script C is going to be linear functions bounded in the unit sphere. This has a nice interpretation in the case when P is a scalar valued predictor, which says that if you have an omnipredictor for sims, then your predictor P is competing against all predictors of the form sigma w dot x when evaluated using the proper loss given by sigma. In other words, for any choice of sigma of the link function, our prediction is up to a small error epsilon beating any predictor of the form sigma w dot x when evaluated using the proper loss definition. Okay, so what was previously known about this problem? Zooming out a little bit, the original work that introduced the definition of omniprediction showed that a general recipe can be constructed for omniprediction through the notion of multi-calibration. Now, multi-calibration is another recent learning theoretic definition, which comes from the algorithmic fairness literature. And the rough idea of multi-calibration is that your predictor should agree with the ground truth when conditioned on various conditional distributions. And the more conditional distributions you agree upon, the closer you are to the ground truth. And in particular, by using a weighted definition of multi-calibration, where the conditional distributions are sort of governed by weights given by the loss function script L and the comparator class script C, a previous work showed that you could achieve multi-calibration by agnostically learning this comparator class via an iterative boosting procedure. Now, one trouble about this general recipe is that it's computationally inefficient in many interesting regimes. In particular, even in very simple cases, such as half spaces, which are an instance of a non-Lipschitz link function given by the sine function, this definition is actually, it's known to be computationally intractable to achieve multi-calibration via agnostic learning. In particular, under complexity theoretic assumptions, this is known to be NP-hard. Now, to make this definition more algorithmically tractable, previous work in ITCS 2023 showed that a set of weaker conditions suffice beyond multi-calibration. In particular, they showed that if you define a set of statistical tests parameterized by the comparator class script C and the loss function family script L, and you pass all of these statistical tests, then all of a sudden you've achieved omniprediction. So roughly speaking, you can consider these statistical tests as showing that your predictor satisfies two more standard notions known as calibration and multi-accuracy. I won't define these in detail in this talk, but these are essentially the key ideas used in this reduction. Now, for the specific family of mommy predicting against sims, applying this existing recipe achieves a polynomial guarantee in terms of various problem regularity parameters, but the runtime is and the runtime and sample complexity are rather large. In particular, the sample complexity scales as something like 1 over epsilon to the 10. And the reason for this complexity is due to the rather iterative nature, black box nature of this reduction. In particular, they use the squared loss as a potential function, and they show that if you iteratively calibrate or make multi-accurate the residual prediction over and over again, then eventually this terminates. However, the sample complexity and runtime of this algorithm are rather large in terms of the concrete polynomial, and moreover, the actual hypothesis that the output is quite complex. In particular, it lacks much of the structure of these single index models that we were trying to predict in the first place, and they can be highly improper with a large sequential depth. So this draws into question questions of interpretability, namely these are not actually related to the single index models that we were trying to omni-predict in the first place. Okay, so I want to also survey some other related results in terms of learning sims in the squared loss, a more popular notion in the learning theory literature. In the realizable setting, where you actually have a sigma and W pair that fits the predictions, the labels perfectly, it's known that a simple algorithm known as the isotron learns sims in the realizable setting in the squared loss. And the algorithm is extremely simple. It simply alternates gradient descent and isotonic regression. In fact, we'll see a definition shortly. One nice thing about the isotron is that in the realizable setting, it outputs proper hypotheses rather than improper. Okay, on the other hand, in the agnostic setting, the guarantees of sim learners are somewhat weaker. In particular, a pair of recent works gave a set of constant factor learners, which under mild regularity conditions approximate the squared loss up to a constant factor. However, the quantitative dependence on these regularity conditions is rather large again. In particular, the sample complexity overhead of one of these recent learners, the state of the art currently for squared loss, has an overhead of something like kappa to the 44, where kappa is the bi-Lipschitz condition number, namely the ratio of the Lipschitz parameter to the anti-Lipschitz parameter. Okay, so this begs the question, are there, end-to-end sample efficient guarantees for learning sims, perhaps in weaker notions of learning than squared loss? And our main results answers this question affirmatively. It says that there's an omni-predictor for single index models using the definition I described earlier, which for beta Lipschitz link functions uses beta squared over epsilon to the 4 samples to learn an epsilon omni-predictor. And we're able to improve this slightly to beta squared over alpha squared epsilon squared when the link function is further assumed to be bi-Lipschitz, namely it has an anti-Lipschitz parameter as well. And one upshot of our algorithm is that it's very runtime efficient. In particular, it runs in nearly linear time, something like nd times 1 over epsilon squared, where n is the number of samples and d is the ambient dimension. Finally, I want to mention that our actual omni-predictor outputs a set of 1 over epsilon squared sufficient statistics in the form of a prediction, a vector value prediction. In particular, this has a multi-index model form where each statistic that we output is the output of a single head composing a link function with a weight vector. So this is what we mean by omni-predicting single-index models using multi-index models. The algorithm turns out to be extremely simple, and it's based on slight modifications to the isotron with a custom isotonic regression solver and a new post-processing procedure. So we call this the Omnitron. I want to mention briefly a few of our other results in the paper, in particular for an empirical risk minimization version of omni-prediction, where we no longer posit that the samples are drawn from a distribution, but rather we just want to output a frequentist estimate. We achieve a slightly better runtime and sample complexity depending on a second moment bound rather than an almost sure bound. And finally, for the simple case of one-dimensional omni-prediction, we have an interesting interpretation of a a known result that shows that simply two single-index models suffice to learn a omnipredictor. There's an open question here, which is that is there a proper omnipredictor in any of these settings, even in the one-dimensional case? Okay, so now I get to tell you a little bit about our algorithm. Um, I'd like to start by introducing the isotron algorithm, which is summarized cleanly in this picture. Intuitively, it's just the merging of isotonic regression with stochastic gradient descent. And the role of each of these steps, the isotonic regression steps and gradient descent steps, is simply an alternating procedure, one of which tries to fit a link function to the current weight vector W, and the other of which takes a gradient descent step using the current link function sigma to update the weight vector W. So the entire algorithm is described in this one slide. And to introduce some notation, so throughout this talk, we're only going to consider two types of losses. There's the squared loss, which has the standard definition here, as well as the matching and proper losses that I defined earlier, which are induced by a given link function. So one thing to note is that the gradient of the matching loss has this nice form where it's the the product of the current feature vector, which comes from the chain rule, as well as the current residual sigma w dot x minus y. So intuitively, this is coming from the fact that the matching loss is an integral. So we're just applying the fundamental theorem of calculus and the chain rule here. This definition might be a little bit fast, but feel free to pause the video and come back to this point if you're ever lost. Okay, so how is the isotron analyzed in the realizable setting? The first idea is that we can separate out the analysis of the gradient descent steps using standard analyses of projected gradient descent or stochastic gradient descent by regret minimization. This is a standard well-known guarantee, and this just comes from the fact that we're optimizing, a function against the sphere over and over again, and we're applying standard regret guarantees here. Okay, so how are we going to actually bound this term in a meaningful way and relate it to something like the squared loss in the realizable setting? The first move is to just apply the definition of the gradient of the matching loss. So as we recalled earlier, the gradient is simply x scaled by the residual ptx minus y. So here we're using ptx to mean the predictor that we're using in the tth iteration of isotron. Now, the first step we're going to use is to simply rewrite this by adding and subtracting a term that intuitively can correct for the fact that, perhaps the true link function was sigma, but we're not using that. We're using sigma t, which is a link function that we learned from samples. Okay. So there's only two lines to analyze here, and they turn out both to be fairly straightforward in the realizable setting. So first of all, the second term can be related to the excess squared loss simply because sigma is Lipschitz. In particular, for a Lipschitz function sigma, you can see that the prediction, the left-hand side is simply ptx minus y, and sigma inverse ptx minus sigma inverse the expectation of y. So using Jensen's inequality and the realizability assumption, as well as Lipschitzness of sigma, it's straightforward to see that this term dominates the squared loss. On the other hand, for the second line, we can actually just show that in the population level case, this is actually just equal to 0. And intuitively, this is a property of isotonic regression. In particular, it's known that the isotonic regression solution is calibrated. And what calibration means is that conditional on ptx, expectation of y is actually just equal to our prediction. So iterating expectations shows that this term is just 0. Okay, so combining these two derivations, we've shown that the regret bound in a single iteration is an upper bound on the excess squared loss. In particular, telescoping this over t iterations, we can show that at least some iterate achieves at most epsilon suboptimality gap in the squared loss. So that's the entire analysis of isotron in the realizable setting at the population level. Okay, so what happens when we move to the agnostic setting? This is a key challenge that was asked and partially addressed by several previous works, and we give a new interpretation of this. So the first observation is that the second line mentioned earlier is actually still non-negative, even in the agnostic setting. So this is this appeared in a previous work based on analysis of isotron in the realizable case. And intuitively, this comes from the first order optimality conditions of this curve fitting problem. So recall that in every iteration, we're solving a curve fitting problem in order to estimate sigma t from samples, and in particular, sigma itself could have been such a monotone function, so it's competing against the sigma that we actually output, and if you actually look at the KKT conditions for this, it shows that this term is always non-negative. On the other hand, consider the third line. This is sort of the thing that we related to the squared loss in the realizable setting. However, in the agnostic setting, we don't have any relationship between y and w dot x, so it's sort of unclear a priori how to analyze this term. So we actually go ahead and define this term as our key notion of a gap guarantee, and we call this term the omni gap. So for predictor P, we define the omni gap of P to be the supremum over all possible choices of the linear weight function W and a monotone link function sigma of exactly this term that we don't know how to deal with in the isotron analysis. So this is the omni gap. Now, one key observation is that the ground truth P actually has zero omni-gap. In particular, if we define P to be the ground truth expectation of Y given X, then simply iterating expectations shows that the omni-gap is zero. And inspired by this, you can think of each set of W comma sigma as a single statistical test. And the interpretation is that if you have a small omni-gap, then your predictor P passes many of these statistical tests. So this is related to these earlier notions of outcome indistinguishability used by previous omni-predictor recipes. Intuitively, these two terms on the right-hand side exactly correspond to these notions of calibration and multi-accuracy used in the earlier work. And in particular, a theorem implicit in the prior work shows that if the omni-gap is bounded, then you have a omni-predictor for SIMS. So putting together these results basically immediately implies our agnostic learning guarantee, at least at a population level. So here's a short proof of the aforementioned theorem. I won't go over this proof here, but it essentially goes through this notion of outcome indistinguishability that I mentioned earlier. And feel free to pause the video and digest this proof more carefully using the earlier definitions. Okay, so this notion of omnigap has turned out to be useful in other settings as well. In particular, in the one-dimensional case, we again rely on this new definition to yield a simpler proof of the optimality of a simple algorithm for isotonic regression, known as the pool-adjacent violators construction. And this is a key ingredient in showing that in 1D, two single-index models suffice to omnipredict. Now, putting together all of these pieces requires a little bit more care in the finite sample case where we don't have population-level statistics. But essentially, the randomness used via samples in the gradient descent steps is handled using standard adaptive stochastic optimization tools. So for the rest of the talk, I'm just going to talk about how we output a link function from samples that approximately optimizes the squared loss. So this is the curve fitting step of the standard isotron. And finally, the predictor that we actually output is simply the family of sufficient statistics outputted by all the single index models that our algorithm has learned so far. And our post-processing function is just a simple averaging composed with the inverse of sigma. Okay, so in the last part of the talk, I want to briefly mention how we make this algorithm efficient and analyze the sample complexity. So the first thing to note is that our regret minimization proof is already tolerant to a little bit of error. In particular, our goal is actually just to find something that is roughly satisfies the KKT conditions up to an additive error of epsilon. So our goal is to find a sigma hat from samples that approximately solves the curve fitting problem. And one thing to note is that if we had outputted the population level isotonic regression solution, that would have sufficed with a bound of 0 on the right-hand side, but of course that's intractable from finite samples. So what we show is that if we slightly smooth the family of loss functions we care about to create some sort of by Lipschitz regularity, this doesn't affect the omniprediction guarantee by very much. And at that point, we can bound the stability of this entire expression in terms of how close we've learned sigma, and the resulting sample complexity follows from an application of Dudley's generic chaining theorem. Okay, so the last piece of our algorithm is how do we actually solve this isotonic regression problem in nearly linear time? Roughly speaking, this is the problem we have to solve. We want to fit a family of 1D points using um, a Lipschitz and bi-Lipschitz uh, curve. So in particular, our goal is to output V's that approximate Y's in squared loss, obeying these sort of Lipschitz and anti-Lipschitz constraints. And I want to mention that this previous computational problem has shown up in prior works, but those algorithms that these prior works used were not linear time algorithms. Okay, so prior works were able to solve this problem inexactly using roughly n squared time. And we give a simple dynamic programming based solution that runs in nearly linear time, n log squared n. And roughly speaking, the idea is to maintain the solution via a piecewise quadratic that we update one at a time. This algorithm is heavily inspired by our prior work joint with Arun Jambalapati on solving a simpler problem known as calibration testing. And our algorithm basically generalizes this from a piecewise linear function to a piecewise quadratic function. Okay, so I wanted to conclude with a few thoughts on follow-up directions to this work. So, a couple of natural questions followed by just considering more general structured families and more complicated types of predictors. For example, you could ask for predictors in settings where the labels do not just take on, discrete valued predictions, but rather real values. This is the regression setting. Another question is what happens when we increase the number of classes that the label can contain? That's the multi-class setting, as well as more general questions of multi-objective optimization, which have been linked to omniprediction in the past. Another question is this notion of propriety. So in particular, our omnipredictor is closer to a proper omnipredictor than prior works. However, it still outputs a multi-index model, and the question of is there a single index model that can omnipredict single index models remains open. We give some partial characterizations in our paper, but as far as we can tell, there's no positive or negative results implying that a resolution to this question. And finally, a major motivation for this entire line of work was the relationship between omniprediction and notions of multi-group fairness. And we are interested to see if, these simple practical algorithms for omniprediction can lead to improved practical performance in empirical settings. Great. So thanks a lot for listening to our talk. And yeah, feel free to get in touch if you have any questions.